In this video, we'll be talking about some properties of the matrix operations of addition, scalar multiplication, and matrix multiplication. Now, as far as properties for matrix addition and scalar multiplication go, first let's go ahead and let A, B, and C be n by n matrices, and let C and D be scalars. Then we have that matrix addition is in fact commutative. So what that means is that if you add two matrices A plus B, it's the same thing as adding it as B plus A. Secondly, we also have that matrix addition is what's called associative. Namely, we have that A plus B plus C. If we add B and C first and then add A on the front, it's the same thing as adding A and B first and then adding C. We also, as far as scalar multiplication, we have that scalar multiplication is also associative. Namely, if we do C times D as scalars first and then do the scalar multiplication into A, it's the same thing as doing the scalar multiplication of D into A and then C into that result. We also, as far as scalar multiplication, we have the following interesting identity. We have that 1 is in fact the scalar multiplication identity. What that means is that if you take 1, the scalar 1 times A, you always just get A back. Now that may seem pretty obvious, and in fact it is, but it's still really interesting because as we've learned with identities, identity is anything that when we multiply by it, we just get back the same thing that we started with. Here, we also have the following. We have two different distributive properties. We have both that the scalar multiplication by C distributes into the matrix addition. We also have that the scalar multiplication of C plus D distributes into A, or namely A distributes sort of backwards. You sort of have A distributes into the scalar addition. Now what this really means in practice is this helps us figure out how to add various expressions. Namely, if we want to evaluate this expression, what we have here is we know that because of the associativity, it doesn't really matter what order we add these in. So we can add in whatever order we want, okay? So that may not seem like a big deal, but it's just one less thing to have to worry about, basically. So here, if we add these, we would have, we know it doesn't really matter, so we could have 1 plus negative 1, so minus 1 plus 0 plus 2. Here we would have 2 plus negative 1 plus 1 minus 3. And here we have negative 3 plus 2 plus 4 minus 2. And so what do we get? Well, we're going to get 0 plus 2, so 2. 2 minus 1 is 1. 2, negative 1. Negative 1, 3, minus 1 is 1. And there we have it. And now it's your turn to try an example. So go ahead and evaluate the following addition of 3 matrices. On the count of 3, I'll reveal the solution. 1, 2, 3. And there you have your result. Let's do another example, this time using the distributive property. Let's go ahead and evaluate the following expression. And here I'm going to do this in 2 different ways just so we can make sure that this actually gives us what we think it should give us. Here, if we go ahead and we just evaluate it like normal, we would have 3 times, if we do the addition first, we have negative 2 plus 4, 0 minus 2, 4 plus 3, and 1 plus 7. And so that would be 3 times negative 2 plus 4 is 2. Negative 2 plus 4 is 2. Negative 2, 4 plus 3 is 7. 1 plus 7 is 8. And so distributing through, multiplying by 3, we would get 6, -6, 21, and 24. Now what if we did it the other way? If we did it the other way, that would involve distributing first. So that would be 3 times -2, 0, 4, 1 plus 3 times 4, -2, 3, 7. That's a 2. And distributing through, we get -6, 0, 12, 3 plus 12, -6, 9, 21. And then adding those, we get +6, -6, 21, and 24. And we notice that we get the same answer. This isn't really a proof of the property, but it definitely shows that the distributive property works in this example. Now it's your turn to do this. I don't care which of the two ways you do it. You can evaluate it either of the two ways. I'll show both of them. And on the count of 3, I'll reveal what that is. 1, 2, 3. And here you have the solution. Now, in a sense, what we have here is some sort of a matrix algebra. So, for instance, for real numbers, we know that the number 0 is the additive identity. The C plus 0 equals C for any real number or scalar C. In a similar way, if A is an n by n matrix and 0 is the n by n matrix consisting entirely of zeros, then A plus 0 is A. Namely, if I write that in, you can see this. It's, for instance, if I had A equals some A, B, C, D, plus the 0 matrix in this scenario would be 0, 0, 0, 0. This would be A, this would be the 0 matrix. Then we expect A. Well, of course we get that. It's A, B, adding individually, C, D. If we were to do a bigger matrix, I mean, we could do this with a 2 by 3. We could really do this of a matrix of any size. So if I had A, B, C, D, E, F, for instance, as my matrix A, plus the corresponding 0 matrix of the same size, this would still be A, B, C, D, E, F. And so we still get A back, right? And again, that's not very surprising. But if we put all of these sort of similarities, you mix the, if you sort of mix together what we did before, we have a sort of matrix algebra that we can do putting all these together. So let me elaborate a bit on that. Really, we know that at the very start of this course, we listed a bunch of properties of the real numbers. And what we notice here is that matrix, at least addition and scalar multiplication, behave very similarly to those, which means we have a sort of algebra we can do. So let me give an example. For instance, if we had sort of for real numbers, if we wanted to solve x plus a plus b, or equals b, x plus a equals b, so this is for real numbers. For real numbers, if we want to solve that, we would add the inverse of a to both sides. So the negative, right? X plus negative a equals b plus negative a. But what we see now is those will just give us 0. So we get x plus 0 equals b minus a. That's the definition of subtraction. And so we have x equals b minus a. If we do this with, but we could do the exact same thing with matrices using our properties that we've talked about both in this and the last video. Namely, if we had matrices x plus a equals b, so we could add the negative of a to both sides, which would give us x plus a plus negative a equals x plus equals b plus negative a, sorry. But then those would give me x plus the 0 matrix. That would be b minus a as matrices, and so I'd have the matrix x is equal to b minus a. So speaking of algebra, let's go ahead and try solving an equation this way. So to solve this equation, 3x plus a equals b, we could say, okay, well, here, let's be really careful and do the algebra, and then we'll plug in the numbers, okay? So here we have 3x plus a equals b. To solve that out, we can apply the inverse of a to both sides, so that would be 3x equals b minus a. And by doing that, by adding the negative of a to both sides, we now have this. Well, here we can multiply by the scalar multiplication on both sides, and so that would be x equals 1/3 times b minus a. And now all we have to do is solve out for, is actually plug in all the matrices. So we have x is equal to 1/3 times b, which is -3, 4, 2, 1, minus a, which is 1, -2, 0, 3. So this is going to be, I'll go ahead and do the addition first. Doing the addition first, we'll get -4. 4 minus -2 is 4 plus 2, so 6. We'll get 2, that's a -2, and then a 4, a -2. There we go. And then if we apply 1/3 to everything, we get the matrix -4/3, 2, 2/3, and -2/3. And now it's your turn to try an example, so go ahead and solve for x in the following equation, similar to how I did before. On the count of 3, I'll reveal the solution. 1, 2, 3. And here we go ahead and we solve for x using our matrix algebra first, and then we just plug things in and evaluate. In a similar manner, we have several properties that follow for matrix multiplication as well. Namely, if A, B, and C are matrices and C is a scalar, then we have that matrix multiplication is associative. Namely, if we do B times C, then put A on the front, we get AB times C. We also know that matrix multiplication distributes on the right. When we multiply by A on the right into an addition, it distributes into the addition. We also know similarly that matrix multiplication is right distributive as well. Namely, if we do multiply by C on the right, we get C, A plus B times C equals AC plus BC. And you may say, well, why do you need to do two separate? Well, the problem here, and this is a big deal, I'll mention the last property in a moment, but first I want you to notice that matrix multiplication is in fact not, matrix multiplication is not commutative. Here we see, again, matrix multiplication is not commutative. Namely, if we take the matrix 1, 2, 3, 4 times -1, 0, 1, 1, in that order, we get 1, 2, 1, 4. But if we swap the order that we multiply in, we get a different matrix. So that's very important to note. And now, as a final property, we also have that both matrix multiplication and scalar multiplication associate with one another. Namely, if we do a scalar multiplication after a matrix multiplication, it's the same thing as doing the scalar multiplication, then that matrix multiplication, or doing the scalar multiplication with the second matrix and then doing the matrix multiplication. Matrix multiplication also has an identity matrix. This will be a lot more important in a couple more videos. We'll look at this further. But for now, we're just going to note that if you have an n by n matrix that consists of 1s on its main diagonal and 0s elsewhere, this is called the identity matrix of dimension n by n and is denoted by In. Namely, we have here the n by n matrix where n rows and n columns, so there's n rows and in columns. And here we have ones along the main diagonal, but zeros everywhere else. And note the reason why this is the reason why this happens is because we have AI. If we have any matrix A times I will be A, and I times A will be A. For example, if we do the multiplication with the identity on this side by this matrix A, we get A back, and if we did it on this side, on the other side, flipped around, we get A back. And again, we need to do both sides because, again, matrix multiplication is not commutative. For more practice in working with these properties and matrix operations, be sure to see the textbook pages 564, 565 and work the suggested problems. In our next video, we're going to look at some applications of matrices.